Welcome to the next video in this series on condensed matter theory. In this video I want to talk about an example where we have three p orbitals, the px, py and pz, on a one-dimensional chain and look at the tight binding Hamiltonian that follows. So we have a lattice where we have a distance a between our lattice points, and it's a one-dimensional lattice. We have a local basis where we have either the px, the py, or the pz orbital per lattice side, and we'll put our coordinate system such that z is in the direction of the one-dimensional chain, and then this is the px and that is py, to make sure that we have a right-handed coordinate system. And let me color in the phases again. So the px orbital is going to give me a pp pi hopping, which is smaller than 0. The py orbital is giving me a pp pi hopping, which is smaller than 0. And the pz orbital is giving me a pp sigma hopping, which is larger than 0. And conveniently, there is no hopping between orbitals. So we immediately can see that our Hamiltonian is diagonal in orbital space, so I only have to diagonalize it in crystal momentum space to immediately find the eigenstates that I have. And then we can use that the pp pi hopping is smaller than 0, just like the hoppings that we had before, and the pp sigma hopping is larger than 0. So we can write down our hopping of our Hamiltonian first in real space. And in real space we have three Hamiltonians. For the pz orbital is a sum over all lattice sides. The on-side energy epsilon pz, a dagger pzr, a pzr, plus pp sigma, a dagger pz r plus a pz at r plus the Hamiltonian conjugate. And then we have a very similar Hamiltonian for the px orbital, sum over all lattice sides, epsilon px, a dagger pxr, a pxr, plus, and now we have pp pi, a dagger pxr plus a pxr plus Hamiltonian conjugate. And for the py, we have just the copy of the px, but of course the index px replaced by the index py. We can now Fourier transform to go to k-space. If you do this, then you get an e to the I k r times e to the I k prime r, which becomes a delta function between k and k prime, such that only one k vector remains, and you get an e to the I k r of k dot a on top of that, because this is a kr, that's a kr plus a, so this e to the I k a remains, which means that our Hamiltonian for the pz orbital in k-space is a sum over all reciprocal, sum over all k vectors, epsilon base pz plus 2 pp sigma cosine ka, and e to the I k a and e to the minus I k a dagger pz k a pz k. And very similar for px, an epsilon px plus 2 pp pi cos ka, a dagger pxk And for the py orbital, exactly the same, but now acting on the py orbital. So we can now draw our energy momentum dispersion or the band structure as a function of crystal momentum, epsilon k minus pi over a at 0 for the px and py orbital. That is a cosine-like dispersion with a bandwidth of 4 pp pi. And as pp pi is negative, we have the minimum at the zone center. We can do the same for the pz orbital. Oh, I'm awfully not centered, but well. So that is the pz orbital, and we have a bandwidth of 4 pp sigma. Yes. And pp sigma has the opposite sign and is most probably larger because the orbitals point more towards each other. So with one electron in the orbital originating from px or py, you'll find that you have electron-like bands. With one electron in the pz orbital, you will find that you have hole-like bands. So you immediately see that once you start filling a p orbital, you should expect to find not only electron-like bands, but also hole-like bands. And if you look in the periodic table, then you see that, well, you start for these elements with an s electron in the principal quantum shell that we have. And then the second electron goes into a p orbital. So it is the second electron that starts to see p-like behavior, where you can get hole-like bands. Now you have to include that these crystals don't form in one-dimensional chains, but in three-dimensional systems, that they're not simple cubic. But nonetheless, this gives rise to the option to have hole-like bands in that system, starting from a tight binding model. Very similar as what you saw in the free electron-like model. You should be aware, it doesn't matter if you start from plane waves or atomic wave functions. They are Fourier transforms of each other, and it's a dual representation. So anything you can do in one representation, you should be able to explain in the other. And here we see indeed that these these bands originating from p orbitals can get hole-like bands just because the inversion symmetry that you have in the p orbital, or the odd parity that you have in the p orbital. Thank you for your attention. We see each other in the next video. Stay healthy.